All right, let's try another optimization problem. This one has a couple of quirks to it, which I think makes it interesting and worth doing an example of. So find the area of the largest rectangle that can be inscribed in a semicircle of radius r. Give it a shot. See how far you can get. But I'm going to go ahead and try this. So it helps if we know what a semicircle is. A semicircle is just half a circle. Okay. And I think there's a trick to making this a little bit easier, which is to go ahead and put it on the coordinate axis. Okay. So now we want to inscribe a rectangle. So that means that it fits inside. Just like that. Okay. Here is a trick that it makes this problem a lot cleaner to work through, which is we are on this semicircle of radius r. Let's go ahead and label that r right there. And then let's just go ahead and pick out a point, x, y, where it touches my semicircle. So this is an example of where actually putting some shapes on a coordinate plane can, I think, make your life a lot easier. It's not mandatory, but I think it works out a lot cleaner. So if you were just having trouble getting started, maybe try to start from here. But again, I'm going to keep going. So looks like we want to optimize the area. So I need a formula for area. I think I got this one. A equals, now normally it's base times height. Let's be a little careful here. My base is actually 2 times x, right? Because there's it's x wide here and it's x wide there. And my height is going to be y. So that is my area. Now, we definitely have some constraints here. My constraint has to do with where xy is allowed to be. So xy is on my semicircle. This is where having it be on the coordinate axis makes our lives a lot easier. To be on the semicircle just means that you satisfy the equation for your circle. What's the equation for a circle of radius r? X squared plus y squared equals r squared. It's our old friend Pythagoras, right? I don't know when's the last time you thought about this, but the equation for a circle, the definition of a circle, is the set of points a given radius from a center. Well, how far is that radius? That's given by a right triangle, right? So if this is x and this is y, at least if that radius is centered at the origin, then all we're saying is that that distance, that right triangle, needs to satisfy x squared plus y squared equals r squared. Yeah, that's where that equation comes from. By the way, for some reason, people seem to not know the definition of a circle, the set of points a given radius from a center point. So those all fit together. If you hadn't thought about that in a while, hopefully that's a friendly reminder. But this is now our constraint. All right, so I'm going to go ahead and solve for one of these. It doesn't really matter which one. I'm going to solve for y. So I get y squared equals r squared minus x squared. And then I get y is equal to the square root of r squared minus x squared. You might ask, hey, don't I need a plus or a minus there when I take that square root? And the answer is no, because we know y is positive. Okay, we solve for y, so that means we get to get rid of y. How? By plugging in. Or substituting is probably a better word for this. A is equal to 2x, and instead of a y, I write the square root of r squared minus x squared. R in this case is just a constant. It's just some fixed number that we don't know yet. We're going to kind of make a formula for this. All right. We did all that setting up. Let's do the calculus part. Let's find, I think we want to find the max, the biggest area possible. So I'm going to take dA dx is equal to, I got to do a product rule here. So I get 2 square root of r squared minus x squared plus 2x times 1/2 r squared minus x squared to the negative 1/2. That is my derivative of a square root when I think of a square root as 2 to the 1/2. You could have always write that as 1/2 root of all that stuff. And then we got to do a little chain rule action here too. Careful, r squared is constant, so my chain rule just says that this is times negative 2x. Okay, put a line here to differentiate this. Whew, a little long, but not bad. I'm going to clean that up, and I'm going to set it equal to 0. Find those critical points. So this looks like 2 square root of r squared minus x squared plus that 2 and that 1/2 go away, and there's a negative 2, so let's go ahead and pull out that negative 2. Looks like I get an x squared times r squared minus x squared to the negative 1/2. Okay, so we found our derivative, and we are going to set it equal to 0. Do a little bit of pre-computing here, cleaning it up. Now, there's a trick to solving something like this that we've seen before, which is noticing that this is going to get a lot better if we just multiply both sides entirely by the square root of r squared minus x squared. Because on the left side that's 0, but that's going to cancel out with this term, which is 1 over the square root, and that's going to take away the root here. So the way I can deal with all these negative exponents and roots is just to multiply through. And notice that what I get out is this 2r squared minus x squared minus the 2x squared, and this thing is just a 1 now. Super nice. From here, I think you can probably solve it. I already did some of the work to make sure I did it right. We get minus 4x squared terms, and then we get that we get a 2r squared. So we bring that 4x squared over to the left, we get 2r squared on the right, and then dividing through, I get r squared over 2. When I take the square root, I would get r over the square root of 2. Nice. Okay, we are almost done. We actually wanted the area, not just x, which means that I need to know what y is. Y is equal to the square root of r squared minus x squared. Well, that's going to be r squared over 2. Nice. We already actually wrote what x squared was. It's this thing. Whew, just about there. A is equal to 2 times x times y I'm sure that cleans up a bit. I know it cleans up a bit, but I'm probably going to leave it just like that. We put a lot of work into that answer, and I'm proud of it. Okay, there's a little bit of algebra work here, which hopefully is a good practice or review. But I do want to emphasize how we got this extra power, which was just to put our circle on the coordinate plane, and then to talk about a point on the plane. Because our equations for shapes on the plane are just defining what points satisfy that equation. So our constraint really naturally was just the equation for the circle. That really helped us out. It would have been a bit trickier otherwise. Okay, I hope despite these being a little tricky, they're also interesting and or fun, and that you practice lots and lots and lots. I'll see you all again soon.